Okay, welcome everyone. Thanks for turning up so early in the morning. So we are going to continue with the second lecture of Gourab on diamonds by imagination.
Okay, thank you. So since the audience is kind of split this morning, let's maybe try to keep things a bit informal. So I invite sort of more questions and kind of maybe have a more interactive way of doing this. So I mean, the goal today, which I planned, was to sort of give an informal idea of how to prove basically this theorem. So so in this sense, it's going to be kind of independent, in a sense, independent of what I said yesterday. Basically, what we're going to show that if you have a sequence of graphs with mesh size very small, with some boundary here, so the sequence of temporal lane graphs, which I tried to explain yesterday. But you can forget about temporal lanes, dimers, and whatnot for time being. Just imagine you have a sequence of graphs with very small mesh size, and you have a uniform spanning tree with wired boundary condition on this graph. So imagine all the boundary vertices sort of wired together. And what we want to prove is that the winding of this uniform spanning tree converges. So at every point, we're going to look at the winding of the branch started from this point of the uniform spanning tree, and we want to show that it converges to the Gaussian free field. Okay, so let's maybe write down what we plan to sort of give an outline of proof today. So
yeah, and Gourab, it would be good if you sort of remind us a little more about what winding is, a winding of a UST.
Yes, I'm going to spend a lot of time today, especially on that, because I didn't really define it yesterday.
Yeah,
so,
thanks.
Yeah, that's one of the main things I'll be doing today. So just to have a broad picture in mind, what we're going to do. So you have a sequence of graphs sort of converging. So delta is the is the mesh size, which goes to 0. Okay, and what we want to show is, so you have a wired UST here. Okay, and we are going to let gamma delta z be the, so for any z, let gamma delta z be the branch of the UST from z. Okay, I'm going to give more precise definitions in a minute. What we're going to show is for any test function f, which is simply a smooth function on my domain, okay, to R. Okay, the integral of the winding. So let's say, so let the wind W of gamma delta z be the winding of gamma delta z, which I'm going to define precisely in a minute. Okay, we will show, so we want to show that the integral over d of the winding of gamma delta z, f of z dz, this converges in whatever sense we want. In the end, it's going to be in probability, but let's say for the moment in distribution, to integral over d of a GFF at z times f of z dz. Okay, but this is a GFF with so it's a GFF with a certain boundary condition, which I'm also going to define, called winding boundary condition. Okay, so that's slightly informally what we are going to show. Okay, so I hope this integral sign makes sense. I mean, things are all discrete here on the left-hand side, but use whatever way of defining this integral you want, maybe extend it into a continuous function in a nice way and things like that. Whichever reasonable thing you want to do should work with the proof. Okay, right. So so before defining even winding, even more a high level strategy of the proof, and kind of my goal is to, if anything, try to explain one way of how to attack this problem, because there is a Gaussian free field, which is not really a random variable. It's some distribution, and then here you have something which is infinite in some sense. So I'm going to outline some strategy which maybe will be useful for some other models as well. Okay, not necessarily this particular one. Okay. So what will be our strategy? Well, we are going to so the winding of gamma delta at Z, we are going to divide it into two parts. So here is my Z, here is my curve gamma coming in from somewhere. We are going to cut it off at a certain ball of some radius. Let's call it e to the minus t. And let's say this part of the curve, let's call it gamma Z delta t. Okay. So we're going to cut it off at some ball. So this is the winding of gamma delta t plus some error term. Okay, so the winding of the remaining part we are going to think of it as some kind of error term, which will be the microscopic part of the winding. Okay, now this part, so winding of gamma delta t, we are going to use continuous theory like SLE and so on to deal with this. And the epsilon t delta, the error or the microscopic part, we are going to use the Russo-Seymour-Welch assumption to show at the end that epsilon t delta, okay, so this, both of this depends on Z at the end of the day. So this at Z is independent roughly for different Z. Okay, so that's roughly the idea. And overall, we are going to use method of moments. So we will show that all moments of expectation of the indicator of the winding times f of z to the power k will converge to the expectation of the right thing. So indicator integral of the GFF fz whole to the power k. Okay, so this is the global strategy here.
Yeah. Just one thing. So what should we expect the epsilon t delta z? I mean, what is the kind of correlation one should expect, say, when z1, z2 is at distance, say, some epsilon, depending on delta? So, I mean, how fast do the correlations decay, etc., with distance of epsilon t?
Right. So, so if you want to look at 2 points at a certain distance r, right? So if you have 2 points, okay, let me maybe write it here. So if you have 2 points at a certain distance r, then if we look at balls of radius, say r times e to the minus t around both of them, then the covariance between these two parts should be exponentially small.
Thank you.
In t. Yes, I'm going to give a more precise statement in a minute. Okay, or maybe near the end we're going to get there. But let me get to the question which you asked at the beginning about winding. So this is going to be, now we're going to talk about windings of curves, and this part is going to be extremely elementary. Okay, so all of these things you can do using high school calculus even, but later we're going to see how this fits into our framework. Okay, so in the beginning, let's assume that gamma is smooth. So gamma is some curve. Some curve. So what was it? We looked at the derivative of the curve at a time t. Okay, and so we write this. We look at the argument of this quantity. Okay, and the intrinsic winding of gamma was simply the integral from 0 to 1 of this argument. Okay. And this argument was taken continuously. Right. So, for example, if I look at a curve which sort of goes around a lot like this, then this will have a winding. So this argument, we don't think of it as between 0 to 2 pi. If it crosses the 2 pi barrier, we sort of increase it continuously or decrease it depending on which direction it goes. Okay. So hopefully this definition of winding is more or less straightforward. You can only do it, we can only define it for smooth curves. Okay, so it's important that it's smooth. Since it's only defined for smooth curves, we cannot really work with it, although it is really what takes care of the height gap, and this is the real quantity we're interested in. So we needed to come up with something which was sort of robust to even taking limits, which gives us fractal curves, right? So this gives us to this brings us to this notion of something called topological winding. Okay, so what is this? So it's not something too complicated. What we do is, so if we have a curve, let's say some curve like that, and we have a point P which is outside the curve. Okay, so this is gamma 0, this is gamma 1, and what we want, so P doesn't belong to gamma, and what we want to look at is gamma t minus P, this vector. Okay, and if we look at this vector, again, we look at the argument of this. So write this as something like that, something like this. And if we now integrate over theta, so maybe let's call it theta tilde to differentiate it from the other one. And so if we want the winding of gamma seen from a point P, so we need to introduce an extra point P now. This is simply going to be, well, the integral of theta tilde t from 0 to 1. Okay, again, this is taken continuously. So I hope this makes sense. So for example, if I had a point, say here, in here in the previous picture, then the winding seen from this green point is also going to be very large. Okay, so this is this notion that we are going to use. Now, if this P is always outside this curve, then this winding is actually continuous with respect to Hausdorff topology. So if P does not belong to gamma 0, so if you have a sequence of gamma delta 0, 1, and if P doesn't belong to gamma delta 0, 1 for all delta, then the winding of gamma delta P is continuous in delta. Okay, so I hope as long as it stays away from the point we are seeing the curve. Okay, but this is different from intrinsic winding, right? Because if I have a point here, and if I look at a curve which is like this, of course, the winding of this curve is not going to be very high seen from this point. But if you have some point here, say P prime, then the winding of this gamma seen from P prime is going to be much bigger, at least in absolute value, than the winding of gamma seen from P. Okay, so we need to always fix a reference point for this to work, which is a little bit of payout if we want, since we wanted continuity. Okay, but in the end, we want to relate these two notions. That's because in the end, height gap is the intrinsic winding, or whatever the limit of that is. So we need a lemma, which is kind of an elementary lemma, which says the following. So if you take gamma which is a smooth curve. Okay. Then the intrinsic winding of gamma, so again, it's defined on 0, 1 to R. Then the intrinsic winding of gamma is actually the sum of the windings seen from its endpoints. Okay, so I said that P needs to be outside the curve, but one can also make sense of this. One can define, for example, the winding of gamma around gamma 1 to be just the limit of as t goes to 1 minus of winding of gamma seen from gamma t. Sorry, winding of gamma t, arg of gamma t minus gamma 1. So basically what we want to do is we want to sort of take a, let me write this definition in a neater way. So here it is. So winding of here, winding of gamma at gamma 0 is the limit as t goes to, let's say, 0 plus of the winding of gamma 0 t, sorry, gamma t1 seen from gamma 0. Okay, so basically we're looking at the winding from a point t all the way up to 1 seen from gamma 0, and we're taking a limit as t goes to 0 plus. So if this limit exists, we say that's the winding seen from gamma 0, and similarly winding of gamma from gamma 1 is going to be the limit as t goes to 1 plus of winding of gamma 0 t seen from gamma 1 minus. Okay. So the total intrinsic winding is the sum of the windings seen from the two endpoints. Okay, that's the lemma, and that's the relation we're going to use. Now I want to give you a proof of this because it's kind of fun and nice. So what's the idea? Well, the whole point or the complicacy arises because we want to look at the argument in a continuous manner. Okay, so if you go around some point, you want to say that the argument increases by 2 pi and then maybe decrease if you go wind in the other direction and so on. One needs to sort of take care of all these things as you go from gamma 0 to gamma 1. Okay, but here is maybe a quick trick to prove such things. So so you take your favorite definition of argument, which is in minus pi pi. Okay, and imagine that your curve is in the domain of this argument. In the end, it's not going to matter what we do. Okay, and now define y and let y tilde be simply the winding mod 2 pi. Okay, so let's say we discard all these issues if you go around the 2 pi mark and just always look at it mod 2 pi. Okay, so then if we have a curve like this, and let's say we'll look at this point gamma t. So then what is the winding tilde of gamma 0 t seen from gamma t? Well, I want to look at the sum of the windings seen from the endpoints. I want to look at the sum of the windings seen from the endpoints for this short curve. Okay, so this quantity is simply, so if I call this vector, say vt, well then this quantity is simply going to be minus of vt. Okay, but then you also subtract this arg of gamma prime at t, but actually you need to add plus because if you look at the definition, the winding, I mean, the argument actually needed to be taken in this direction if you wanted the endpoint winding from this point. But here the gamma prime is actually going in the opposite direction. So we added 1 pi. Everything is mod 2 pi for this argument. So that's why we have this. And in the end, it's just minus vt plus arg of gamma prime t. Okay, and if you look at winding tilde of gamma 0 t seen from gamma 0, then this is actually the opposite vector vt. Okay, but now it's minus arg of gamma prime 0 and no extra plus pi because the curve is going in the right direction for at gamma 0. Okay, now if I add these things up, so then winding tilde of gamma 0 t seen from gamma t plus winding tilde of gamma 0 t seen from gamma 0, the vt part cancels up and you get arg of gamma prime t minus arg of gamma prime 0. Okay, so this is not quite what we want. We want r small arg of gamma prime t minus small arg of gamma prime 0. So in the end, we have we can write this as this quantity plus an additive constant of 2 pi times an integer, which is a function of time. So this is in z. Okay, we don't know what it is, but it's some integer. Okay, and we in the end what we want to show is that this quantity, this kt is 0 for all t. Okay, but notice that for small t, kt will be 0 because since the curve is smooth, if t is very small, then you're not going to go around 2 pi for t which is very close to 0. So therefore, for small t, this small arg will actually be equal to capital Arg, and this extra additional error you're not going to count. Okay, so for small t, kt is 0, and both of these functions are taken to be continuous. So by continuity, kt is 0 for all t. Okay, so this shows that actually you can let t go to 1, 10 to 1 minus, and this finishes the proof. Okay, if you let t go to 1 minus, then you end up with this equation for t equals to 1, which is kind of what we want. T equals to 1, arg of gamma prime 1 minus gamma prime 0. Okay. So any questions about this proof? Because the next statements which I'm going to state will basically be, and the way to prove them will be basically variants of this idea of how to go from the usual arg we know about to the args which is taken as continuous functions of time. Okay, so if not, we have related this notion of topological winding to that of the intrinsic winding. Now, one thing that is actually simpler to do is to understand winding seen from boundary. Okay, and if you want to compute that, you can actually use complex analysis definitions, and it kind of works fine because anything in the domain is not going to wind around the point on the boundary a lot. Okay, so if you have some domain which itself winds a lot, then okay, then it's fine. But let's take some domain like this. Okay, and so okay, so this is my d. This is a marked point x. X belongs to the boundary of t. Everything is smooth up to so far. So we can define a function. Let's call it the argument function in D seen from the point X. Okay, such that if you take any point A and B in the domain and connect them by a curve gamma, then argument at A minus the argument at B, this arg dx, okay, is going to be independent. I mean, it's going to be basically you can write this down as imaginary part of some contour integrals. Okay. But what I want to say, so imagine integral over P over gamma. And the point is that this is independent of gamma. Okay. So for example, if this domain was just the circle, if just the unit disk, then you can define a function inside such that the argument sort of changes from 2 pi to 0 exactly at this point. And at any point you can define a function such that the argument will be perfectly well defined. Okay, so arg d1 you can define. So for example, can define arg d1 such that, for example, arg d1 of 0 will be pi, and this completely belongs in 0 to 2 pi. Okay, so seen from a boundary point, there is a well-defined argument, but seen from inside the domain, things get more complicated. Okay, also, just on that same note, if we have a curve gamma with gamma 0 equals to x, then it's not too difficult to believe that arg of gamma prime 0, you can define it as like a limit of the argument for small times at gamma. Okay. The way we are going to use it is we are going to take these UST branches and we are going to sort of always extend it to a certain boundary point 1. So we kind of have always a reference point, and we always count the windings started from this boundary point. And one nice thing about this is that, for almost surely this point here, these curves along the boundary are always going to be smooth. Okay, so the non-smoothness kind of starts once you start entering the domain. Okay, so we have some notions of argument, kind of two notions of argument at this point. Yeah.
What is the convention you follow? I mean, say after you reach the boundary, I mean, you go what, anti-clockwise or clockwise?
We go clockwise. So if for any UST branch, I read the boundary and then I kind of go clockwise all the way to 1. That's going to be the convention. Yeah, this is just to fix something, so we have something concrete in hand. Okay, so just with this definition in mind, if we have the unit disk D and we have this point 1, okay, then the winding. So as I said, we are going to always go towards 1. So if we have this curve like this, then the winding of, so then the winding of gamma seen from this point 1, or let's say this point, let's call this point X because we don't want to fix this 1 for now. For any boundary point, winding of gamma seen from X, well, this is going to be the argument in this domain dx of gamma 1 minus the argument in this domain dx of gamma prime at 0. Okay, and if this x was 1, this argument of gamma prime 0 would simply be pi by 2, for example. So it's a very concrete thing. Okay. Now with this definition, notice immediately that if we want sort of, if the curve was smooth, for smooth gamma, the intrinsic winding of this curve gamma would be winding of gamma seen at gamma 1 plus this quantity, which we have here. Okay, and the idea later will be to define a quantity which is going to sort of emulate this quantity. Okay, so it's going to be the winding seen from gamma 1, and we're going to add up these quantities here just so it looks like the intrinsic winding, although this curve ceases to be smooth once it enters the domain. But we're going to define it anyway, and we are going to continue from there, and we'll see that this gives us the right thing. So before that, still we're with smooth curves. We also want to kind of know what happens if we apply a conformal map to a curve to its winding. Okay. Now, I know that I said that UST is conformally invariant. So if you start with a UST branch at Z, and if you apply a conformal map which maps Z to Z prime, then you get another UST branch seen from Z prime. Okay, but the windings undergo a certain change, and that certain change we want to pin down what that change is. Okay, because later we are going to push out lots of UST branches in order to understand how it affects the winding. Okay, so for this we need this following. We need to understand how the winding changes under application of conformal maps. Okay, now let's again start with intrinsic winding because that's kind of easy to understand. So the intrinsic winding, so let's say psi is a smooth curve, conformal map. So let psi be some map from D all the way to D prime. Okay, so let's say it maps dx to D prime. So let me just want to make sure I have the right formulas here. Yeah, so let's say it maps to D1 prime 1. Okay, then so we want to understand the intrinsic winding. So okay, so we have a domain D and some X here and some gamma. Okay, so which looks something like that. That's kind of a typical application. Okay, and then I apply psi, and I'm going to get some. I'm going to get some other domain D prime, and I'm going to have some 1 here, let's say, and some other function psi of gamma. Okay, so this is gamma. Okay, so the intrinsic winding, okay, that's too thick. So the intrinsic winding of psi of gamma, how do I compute this? Well, this is going to be integral from 0 to 1. Let's say the parametrization is still from 0 to 1. Okay, so gamma is 0, 1 to D. Of arg of psi of gamma prime of T. Okay, and in the end, this is going to be just the chain rule. So we're going to write it as arg of psi prime of gamma T plus arg of gamma prime T, Tt. Okay, and this is arg of psi prime of gamma 1 minus arg of psi prime of gamma 0. So this is the additional thing that we add. Plus, if this quantity is simply the intrinsic winding of gamma. Okay, so what did we learn? We learned that as long as the curve is smooth and psi is conformal, then we have the change in winding of psi of gamma is going to be simply given by this quantity. This is the error. Okay. Now, if in the typical application, this x and 1, x is going to map to 1. So this point is going to be a fixed point. So even this quantity is going to disappear because it's not changing there. It's nearly really like identity. So it's going to be 0 here. But this is the quantity that's going to define the change in winding as we apply a conformal map. Okay. Of course, in case of the topological winding, you need to be a little bit more careful because we're seeing things from a point. But so that's the kind of details I kind of want to skip here. But one can make sense of this. So we can extend this change of winding formula for topological windings as well. And what do we get? We get this following lemma that winding of psi gamma around psi z. So if we have some gamma and some z, maybe the endpoint, maybe outside, but really this is the picture that you should have in mind when we are applying the maps. Okay, but this is kind of a general formula. So if we want to understand the difference in the topological winding, well, okay, so we need to look at kind of the main term, which is arg in the domain arg of psi prime z. Now here, let me be a little bit more precise of what this argument is. Well, psi is a conformal map, so psi prime of the domain D does not contain 0. Okay, so arg of psi prime D is some version of argument in the domain which doesn't contain 0. Okay, you can define it up to a global shift of R. Okay, so this is well defined. So psi prime D does not contain 0. So arg of psi prime D is defined up to a global shift of R. Okay, so later we're kind of going to fix what these things are in a proper way, but let me let me be a little bit more abstract here. So we have arg of this plus some extra quantity which comes from the fact that we are actually looking at topological winding rather than the real winding. Okay, now okay, this is all fine, and in fact this lemma is going to work even if you look at a point z, which is the endpoint of gamma. Okay, but now what I want to say is that we want to sort of think of gamma as fractal, and in the end we want to look at the change in winding of gamma seen from a point which was actually the endpoint, but I'm going to cut this gamma off at a certain cutoff point, right? So that was the idea. So we wanted to actually think of cut the gamma off at some ball of radius r. Okay, and actually, if we do that, then if we look at this change of winding under the conformal map, this is going to create a certain error. Okay, and this error is going to be the order. So this error is going to be the order of z minus gamma 1. So the distance between z and gamma 1 divided by the conformal, divided by, oops, sorry. Let's call this small r. Small r. Okay, it looks like gamma. So let's maybe call this small r. So this is going to be the error is going to be of the order small r by capital R, where capital R is basically the distance of z to the boundary, but to be very precise, it's the conformal radius of d seen from z. Okay, so if you don't know what conformal radius is, it doesn't matter. It's just some quantity which is amenable to conformal transformations. It's basically measures in a conformal sense how much z is away from the boundary. Okay, it's some kind of radius. So, okay, moral of the story is that if you want the change in winding of topological winding under conformal maps, this is kind of the main term here, which gives you the change in winding. Plus, you have some extra terms which are here, which comes in because it's the topological winding, plus some error which depends on where you cut things off. Okay.
Just one thing, at some point you're going to make the curve even inside fractal, right? So won't that create trouble about very large amount of winding around Z at a very small scale?
Yes, exactly. So in the end, we are going to think. So let me actually make this remark right now. So this lemma actually works even if gamma is fractal, as long as Z is away from gamma 1. So, so just to emphasize, so you have a gamma, maybe fractal, but it's cut off here at some radius, and you have this sort of target point Z. So the change in winding under a conformal map of this gamma, which is cut off now under the conformal map, is still given by this global thing at still computed as psi prime d, but you have this error term here, which is going to be very small if small r is very small compared to capital R, which means that if this radius is something like conformal radius times e to the minus t, then the error in this so the error when you do this conformal map transformation in the winding, I mean the amount away from this main term when you do this distortion is going to be this. Does that answer your question?
Yeah, no, I'm still a little worried. I mean, what happens if there is the curve could be becoming fractal, right? So, I mean, what exactly is happening at the small scale that is allowing you to, I mean, is there some passing to a limit that is probably hidden somewhere, which I don't see? I mean, basically, say taking a smooth approximation of the continuous fractal curve, and you're claiming that the total amount of winding in a small ball is still remaining estimated by this little r by capital R.
Right. Okay, I see where your objection is. So in the strategy of the proof, what we're going to do is so imagine you have this small mesh size and you have cut off this path when it hits some ball of radius e to the minus t, and you let the mesh size go to 0. So then you have this winding of this path which is cut off, okay? And whatever this path is, even if it's fractal or not, this lemma is just telling us how to compute the change in winding, the topological winding seen from the target point under the application of a conformal map. Okay. Now, of course, this curve is going to wind a lot inside this thing. In fact, infinitely often in each direction. Okay. So later, what we're going to do is we are going to take a limit as t goes to infinity of this quantity, and this is just one of the tools that we need to do that computation. So I'm kind of far from taking the limit yet.
Okay.
This is just telling us how the winding changes for the truncated curves at the moment. That's all. And this is telling us what the distortion is under the just application of a conformal.
Thank you. Yeah.
Okay. So so maybe let me give you a picture of how what a typical application of this could be. I kind of drew it from beforehand. Wanted to. Oh, that's not good. Okay. Okay, sorry. Okay, somehow this thing is crashed. Let me just get here. Okay, so it was here, right? So let's try this again. Right. So a typical application will be of the following form. So you have let's say this curve is gamma and it's cut off at some point, and I've drawn some other UST branches seen from other points. What I'm going to do is I'm going to take a conformal map of this domain slitted by this green part, and I'm going to see how the winding changes if we do that. Okay? This is one of the typical applications of this lemma. Okay. Now, let's get back to the continuum UST, and we'll see how these things could be useful. So just to remind you how to sample a continuum UST, well, you start with the domain. If you want to sample the branches of the UST from a certain number of points, you take a point on the boundary seen from the harmonic as a harmonic measure seen from one point, draw the SLE to that point, and then you start at another point in the slitted domain, draw the SLE to a point seen from the harmonic measure, and so on. Okay, so this is the method of drawing this, and once we have drawn say any number of branches, the law of the remaining branches is simply a UST in the slitted domain. Okay, so let me also say this. This is kind of important. This is some kind of domain Markov property for UST. So given, so let's say gamma 1, gamma 2, etc. Given gamma 1 all the way up to gamma k, the rest of the branches is a UST in D minus all these branches. Okay? So think of another wired UST in the remaining branches. So this is the kind of domain Markov property that we're going to use.
Gourab, sorry to interrupt.
Yeah.
Yesterday you had mentioned something about if you take finitely many pretty large, then the remaining contribution becomes small. Is the reason basically because the conformal radius is shrinking to 0 sufficiently fast? I mean,
yes. So this is, you're absolutely right. And this is not going to be true for a single point. This is kind of going to be globally true for all points. So this is a very important fact actually in the proof. Okay, so I mentioned something in passing at the beginning of this lecture that we will be talking about winding boundary condition. So what that is, and this is going to be important when we talk about imaginary geometry. Okay, so simply if you have a domain and if you have a marked point, then the winding, so you define a curve here. And you simply look at, so let's say this is, and let's say this is some curve which is given by u0t. So we'll basically be looking at u0 to pi. Okay, so then ud, which is the winding boundary condition, is going to be simply the harmonic extension of the intrinsic winding of this curve. Okay, so you take this curve, look at the intrinsic winding at all the points, and look at the harmonic extension of that. Okay, and one can check, and it's probably will not be hard to believe given the change in winding formula that if we have a conformal map, say psi from dx to D1, which so let's say D is this unit disk as usual. Okay, then the winding boundary condition in the domain dx is simply the winding boundary condition in the domain D1 composed with this map psi minus a correction term which is given by this arc term. Okay, so and one thing that you can check. So for example, you can even ask, what if dx is so if we want to understand d1 at a point z which is not 0, well, you can apply a Mobius map which maps z to 0 and keeps 1 to 1, and then you can check using a calculation of the Mobius map that this is actually it's an explicit quantity, and it's given by the argument seen from the boundary for the domain for the unit disk. Okay, so this is going to be slightly useful later for this formula. And now I want to talk about imaginary geometry coupling, or the version or one little piece of this whole theory that we are going to use. Okay, so this whole theory is due to, well, started by Dubeda and then sort of finished together by Miller-Sheffield. So what's the idea? Well, so the vague idea, so the theorem I'm going to talk about is going to be pretty concrete, but the real idea I also want to mention is that we have this Gaussian free field, right, GFF, and what we want to do is want to view sort of the argument of this Gaussian free field multiplied by a constant for all points x in D. So I'm looking at e to the I times h. Okay, it doesn't make any sense, so that's why it's in quotation, because h is, you know, a random function. It's not even a function. But if we do that, then it gives us a vector field. At every point, I have a unit vector pointing in the argument of this h times some constant. And if we view it as a vector field, we can talk of flow lines. Meaning that you sort of try to go along the arrow of this constant times h vector field. Okay, and the point is that the flow lines of this vector field is going to be equal to some SLE curves. Okay, SLE with some kappa, where kappa is going to be some function of this constant. Okay, that's the idea. I mean, the global idea. You want to understand this flow. This flow lines of these vector fields given by a Gaussian free field. Okay, but here is the sort of the concrete theorem that we need, because at the moment this whole paragraph is very vague. So we're going to fix a constant. Yeah.
So I mean, just very naively, I mean, if you have in the smooth case, I mean, just as you were trying to in the previous case, the motivation was given by a smooth case. So suppose you have a smooth trajectory. What you're doing is at each point you're taking a normal unit tangent vector. Is that what this e power I is supposed to mean, or
yes.
Is it a?
So the thing is that the way to think about it maybe is you can find so these are all random curve and fields, right? So
Correct.
The way to think of this is maybe if you think of all of this as smooth, and if the SLEs were smooth, you can couple these two things together in the same probability space, such that the tangent vector of the SLE curves at a point is going to be roughly this quantity to the IC.
Okay, thank you. Yeah,
that's the idea. But of course, this is very far from being sort of shown hands-on. Maybe our theorem will give some idea of how this might be, this connection might be exploited. But here is a sort of a theorem which kind of tells us about this. So fix chi equals to 1 over square root 2. Okay, there's a reason for doing this, because traditionally, if we talk about an imaginary geometry theorem, this chi actually corresponds to this quantity for kappa, for general kappa. But okay, for us kappa is 2, so chi is 1 over square root 2. So there exists a coupling between a zero boundary GFF in a domain D plus chi times this was the winding boundary condition. So it's a GFF plus winding boundary condition on the domain times chi, okay, and the UST, so that the following holds, given a certain collection of branches gamma bar, the law of the field, so let's say this is H in D minus gamma bar is simply given by a zero boundary GFF in D minus gamma bar plus chi times the winding boundary condition in the slitted domain. So this domain Markov property, which I was talking about for the UST, sort of holds simultaneously in some sense for the H and for the field and the tree. Even if you're given certain set of branches, the law of the field in the complement is given by sort of the same field. If you think about that, it's the same field, but in a different domain, which is slitted by these curves. And also, and this is going to be a consequence of the fact that if you reveal a lot of branches, it's basically telling you everything. H is measurable with respect to t, with respect to the whole UST. Okay. Now, the point is that this thing, which it might seem like what this is kind of what we want, except the fact that these things are completely abstract. This is just defined in the sense of harmonic extension of these windings. Okay, so there is no notion of actually using the windings of these curves to define this field. So what we will show is that the winding field will converge to a version to this Gaussian free field. Okay, so this is what we are going to show when we truncate it at some point t. Okay, so let me write down a proper definition. So in this vein, we are going to define H T D at Z. This is going to be the winding of the UST branch at Z up to a time which is okay. So it's capacity T, but you can think of it as the first time you hit the ball of radius e to the minus t around Z. Okay. The real definition is not super important at this point. So it's the winding of this curve up to time t seen from Z plus the argument. So this definition simply emulates the intrinsic winding boundary condition, the intrinsic winding definition. Okay, so it's an emulation of that, and it's also truncated at this point, truncated at sort of ball of radius e to the minus t. And the theorem, now maybe a more precise version, is that this HTDZ, this whole field, converges to a GFF in D, where HDGFF is the intrinsic winding GFF. And there is an additional pi/2 global shift in the GFF. Okay. So this extra pi/2 kind of comes out of the calculation. We kind of made peace with this extra pi/2. I mean, it's not harming anyone. It's just a global shift in pi/2. But the way we are thinking of this pi/2 is that you sort of go, the way we are defining it, you go along the boundary and then you sort of turn into the domain. We are kind of counting that as well. And that kind of accounts for a right angle turn, although it kind of doesn't make sense because it's fractal, but that's kind of the way we interpret this extra pi/2. Okay, so how do we prove such a thing? So let's try to understand the simplest situation. So what is so let's take the domain to be the unit disk. Okay, and okay, so we are always going to think of it as going to the boundary and going all the way up to 1. Okay, and let's think of this at 0. Okay, so let's try to understand what happens to expectation of HT at 0. Okay, so to compute this quantity, well, there will be the winding part. Okay, so let's remember the definition. So it's the winding of this curve seen from Z plus these additional things. Okay, now let's look at what these things are. So this is going to be, okay, so let's write this down. So expectation of the winding of the SLE curve seen at 0 up to time t, seen from 0, okay, plus the argument in the unit disk seen from 1 of 0 minus the argument in the unit disk seen from 1 of gamma prime 0. Okay. Now this quantity, this is an SLE started from a point which is sort of picked uniformly because it's a harmonic measure from the origin is uniformly from the boundary targeted to the boundary. Okay, but by symmetry, since it's kind of, so whatever be this point, it's kind of the law of SLE is symmetric under conjugation or reflection along this point. So a symmetry argument will tell you that this is 0. Sorry, so this is not 0. I mean, this part, the winding of this part is 0. And all that you need is the winding of just the part going along the boundary where this point is chosen uniformly from the origin. Okay. Now, of course, a uniform point from 0 to 2 pi will on average be at pi. So therefore, this winding is just pi. Okay. And this quantity is the winding of 0 seen from 1. So this is also pi. And then you have the winding of gamma prime 0, which is pi by 2. So this actually turns out to be 3 pi by 2. Okay. Okay, so I hope this calculation is okay. It's kind of the simplest thing one can try to calculate here. And the next simplest thing that one can ask is what is the expectation at a point which is not 0, right? So let's now imagine that you have a point which is Z and you have truncated things off. Now, what the idea is to use a Mobius map, which maps from D to D, and psi 1 is 1 and psi Z is 0. Okay, this is a very explicit Mobius map. You can even write things down, and using the change in winding formula. In the interest of time, let me not do this calculation. But you can imagine what to do here. We have the change in winding formula, which works for fractal curves cut off at a point, and we have an explicit Mobius map. So if you use the change in winding formula, what we get is that what we get is even kind of pointwise, that HTZ minus HT0 is minus arg at psi prime of t, okay, at psi prime of z, plus epsilon, plus some error, which is actually of the order e to the minus constant times t. Okay, this you can explicitly compute actually, and from this you can get a calculation. Gives us that expectation of HTZ is going to be twice arg seen from 1 of Z minus pi by 2. Okay, some formula. Well, actually, you need to take the limit because we have this extra error term which you need to go to 0. Okay, and if you look at this formula closely, actually, this is the winding boundary condition at Z plus pi by 2. Okay, so it kind of matches with the mean that we claim in the limit. It's just for the 1-point function. Okay, and now here comes the kind of the key input in order to identify the limit. So what we want to do is now what we want to see how the mean behaves given a whole lot of branches. Okay, so suppose you're given a lot of branches. Okay, so let A be a lot of branches. Okay, and we want to compute so we want to compute what is the expectation of HT at a certain point Z conditioned on A. Okay, so you're given these A branches. What is the mean at a point which is okay, not in A, but we're conditioned on this. Okay, now I want to kind of quickly recall the imaginary geometry conditional expectation. What does imaginary geometry gives? Let me write this in green. That so what we so if we define HGFF to be so 1 by chi times the 0 boundary GFF plus the winding boundary condition. Okay, then the GFF conditioned on A is defined as is given by this quantity. I've just divided by 1 by chi to make the formula a little bit nicer, but it's the 0 boundary GFF on D minus A plus the winding boundary condition on D minus A seen from 1. Okay. This was the imaginary geometry. And I want to claim that you get the same conditional expectation if you do the changing winding formula. So expectation of HTZ given A, actually after I apply the changing winding formula, is going to be expectation of some other independent UST in the domain, in the whole domain D, after you've mapped out all the domains, all the curves by some conformal map G. So okay, so we are going to apply a conformal map GA, which maps D minus A to D. Okay, conformal, and GA of 1, we want it to be 1. Okay, then applying the change in winding formula, we get this is the value of the field at GA of Z. But then you subtract the argument of the I mean, you look at all this error term. I mean, the error term that we got from the changing winding formula. Okay, and now if we take a limit, this actually goes to the intrinsic winding boundary condition plus pi by 2 minus this quantity, and actually this is the same as the intrinsic winding boundary condition at Z. Okay, so the moral of the story is that if you go through this calculation, and kind of believe me, because I believe this was kind of fast, is that the conditional expectation of the winding field is equal to the conditional expectation of the imaginary geometry GFF. Okay, so so we have a GFF coupled with the UST, and we have this natural field winding field coupled with the UST, and what we just claimed is that given, so we can think of the UST in the middle and the two fields on two sides, and this coupling satisfies the property that given a certain finite set of branches, the conditional expectation remains is the same of those two fields. Okay, so this tells us that these two fields should be at least very close, at least in the sense of mean. Okay, and now now what we want to do, if we show that the variance of so let's say HTZ, okay, so it's a bit hard because I wanted to say a few things before I say this, but let me just say something like this. So a variance of let's say the integral of HT bar Z, where we subtract the mean, is very close to 0, then we are kind of done, because we are saying that we have a field which is very close to the field that we want it to go to in mean, given a lot of branches, and the variance of this field given a lot of branches is also very close to 0. So therefore, this field given a lot of branches must be very close to its mean. So therefore, those two fields must be close to each other. Okay. So how to argue this kind of thing? Well, any questions with about the strategy so far? Because this was kind of the main idea of how to identify the limiting field, and this is one of the things that's actually missing in the multiply connected case. So yeah, I hope I could get this point across, at least, of computing the conditional mean. Okay, so I mean, so far we just computed the 1-point function, and if you want to kind of show something like this variance, okay, so variance conditioned on A, of course. if you want to show something like this variance is small, we need to find the k-point functions, okay? Or we want to kind of show the k-point functions have limit. Okay, so I'm going to go a little bit fast now because this part is really technical. So what you need to show is, so we claim, so the lemma is that the limit as t goes to infinity of expectation of htz1 all the way up to htzk, this exists, okay? And why? Well, if you have a set collection of branches, let's say 2 points, and we want to show that this is Cauchy in time, okay? Then what we're doing, if we're looking at the difference in htz1 minus ht prime z1, then we need to look at what the winding is of some small red part, okay? And we kind of want to show that these red parts are independent. So the idea is that the red parts are independent. And why are these red parts independent? Well, again, we apply this change in winding under conformal maps. So what we want to do is we want to map out some branch and try to understand what the change in this field is compared to if we didn't map this out. So, if this has no effect on this change in expectation of this, then these things will be independent. So there's some estimates involving conformal maps, and the point is that since these things are small, conformal maps behave nicely. So therefore, one can argue that this is fine. Basically, arg of psi prime under mapping out this curve or mapping out this curve plus the red curve is the same. That's the idea. So once you show that these limits exist, the next thing that you need to show is some kind of regularity of this limit. So so we need to show some kind of regularity of the limit. Basically, what one needs to show is that if you have these k-point functions, then this is at most some log to the power some alpha of 1 over r, where r is kind of the minimum of zi minus zj. Okay. So even if t goes to infinity, so you can take this is uniform over t. Even if t goes to infinity, this limit behaves kind of in the same way as a GFF would behave if the points come very close together. Okay, so this is the regularity of the limiting field that we need. Okay, and then how do we prove the existence of the limit? Well, then what you need to do is you need to look at integral of htz with some test function fz to the power k, and we want to show that as t goes to infinity, this limit will exist, because if we expand this to the power k, you're going to get some k-point functions like this in the integral, and then you need to exchange limits and do Fubini and whatnot, and dct and whatnot, and get the limits. Okay, so this shows that the limits exist, and once we know that the limits exist, then we apply this. Then we want to show that the variance, the conditional variance given a lot of branches is small. Okay, so now given a lot of branches, we want to show that the variance of so basically this boils down to showing that the integral over d cross t expectation of ht bar z, ht bar w given a, okay, this is small. And just to give a pictorial idea of why this might be small, well, we have kind of drawn a lot of branches. Okay, think of a huge mesh of branches. Now, if you have a z here, and if you have a w here, now if you map out d minus a to the unit disk d, and if you map z to 0, then this W will be very close to the boundary. So if you have psi z equals to 0, then psi of W will be very close to the boundary. Well, simply because the distance between these two kind of it's a measure of how a Brownian motion can reach this W seen from Z. Now, if this is a very bad mesh, then the Brownian motion will have a hard time going through this mesh to reach the W. And that's why when we map it out conformally, you can argue that the W will be mapped very close to the boundary. Okay? And this is the key to showing that this quantity is actually very small. Okay, so after this, it's a matter of putting the pieces together to show that actually the UST show that we can couple the HTZ, the winding field, between HTZ and HTGFF, which is the imaginary geometry coupling, such that in the limit, HTZ sort of converges in probability to HGFF, to this quantity. Okay, so that's the continuous part of this whole argument, and as Mohanda was kind of pointing out, that, well, what happens to this microscopic part? Well, we kind of showed something, right? So we showed, so let's see what we showed. We showed that now back to the discrete case, we have, let's say, 2 points, Z1 and Z2, and we want to understand what happens to H delta Z1, H delta Z2. Okay, and even the bar of this. So H delta Z1, H delta Z2, the bar of this. Okay, so what we are going to do is we are going to truncate them to use the continuous part. So we are going to truncate them. So we're going to write it as HT delta plus the error, which is actually quite big at the moment, times HT delta Z2 plus the error. And then what we want to show is that at the discrete level, epsilon t delta Z1 and epsilon t delta Z2 are independent, roughly. And okay, since these all have bars, I mean, you subtracted the expectation. Now you can say that if you have something which is independent of whatever happens near Z2, okay, and also, and epsilon t delta Z1 is roughly independent of HT delta Z2 and vice versa. Okay, epsilon t delta Z2 is also independent of HT delta Z1. So if all these are true, now if we expand this product, you'll see that since these are mean 0, they're all going to vanish up, and you're going to end up with just HT delta Z1 and HT delta Z2. And now we carefully take a limit as delta goes to 0 and t goes to infinity simultaneously, so that t goes to 0 kind of much smaller, at much smaller pace than delta, arbitrarily smaller. Then overall, this limit is going to be the same limit as this imaginary geometry coupling. Okay, so a final few words about how one shows that these things are independent. Well, here's another theorem, and this actually forms a big part of the paper as well, which is the following, that so we use a sort of multi-scale coupling argument. So there is a coupling between the UST T and independent USTs T1 and T2, okay, such that the T around the ball of radius R around Z1. So given some points Z1 and Z2 around which we want to couple, the portion of T in the ball of radius R around Z1 is the same as the UST T1, and around Z2 of T, around ball of radius Z2 of for T is the same as the UST T2. Okay, so what this means is that we have coupled T around the ball of radius R with the same as T1, and around the ball of radius R of T to be the same as T2. Now the difficult part is we could not do it for a fixed R. Okay, so this R is actually random. Okay, sorry. So this R is actually random. Actually, R has the following relation that it cannot be too small. So if small r is the distance between Z1 and Z2, then the probability that is much smaller than r times epsilon decays polynomial in epsilon. Okay, and this needs a multi-scale coupling argument and Schramm's lemma. Okay, so this shows that these error terms are roughly independent. And even though these terms are actually, if you remove the bars, these are actually going to infinity with delta, since we fixed a t. Since we subtracted the mean and these are independent, they, in the moments, they sort of cancel out and don't bother us in the end. Okay, so I think this is, let me just stop here. I could go on for with more details, but let me not get into all this. Let me say a few words of where we stand with Riemann surfaces. So for Riemann surfaces, what we need to do is we will need to carry out this program, and the idea is to sort of lift everything to the universal cover and kind of use the same ideas that we used in the simply connected case. Now, of course, there are some obvious difficulties. For example, if you are away from your fundamental domain, then you cannot really think of the branches as being generated by independent walks. I mean, once you are outside your fundamental domain, things are completely determined by what happens in the fundamental domain and things like that. So these are the technicalities that one needs to take care of if one wants to go to the universal cover. So we could get around those technicalities and get a conformal invariant limit. But the issue is that we don't have this nice imaginary geometry coupling, meaning that given certain parts of the CRSF, we don't know what the law of the remaining, whatever the limiting Gaussian free field it will be. So that's one thing that's missing. And we kind of all lifted everything to the universal cover and used the same assumptions that we had in the simply connected case. We should sort of lifted them and you assume the similar things to be true on the universal cover. For example, we assume that if you start a random walk on the universal cover, it converges to Brownian motion on the universal cover, which is going to be a unit disk in the most of the hyperbolic setting. So that's the one assumption. And this crossing RSW assumption that we had in the simply connected case, we're going to use it. We said that, okay, so if you lift everything to the universal cover and look at a compact set, for small enough delta, depending on the compact set, you cross the rectangle with uniformly positive probability, things like that. Okay, so so that's where this whole project stands. So one way to identify the limit in the Riemann surfaces is to either develop imaginary geometry or prove that the limit is what you expect it to be for your favorite collection of lattices. But both of them seem hard at the moment. So at the moment, the smaller goals is to do it for simpler cases like the annulus or the pair of pans, and maybe go from there. That's kind of where this whole program stands. Okay, so let me stop here. Thank you for your attention, and if there are questions, I'll be happy to take them.
All right, so let us thank Gourab for the series of 2 talks. It's a great talk. So, are there any questions?
Yeah. So, for the Riemann surface case, instead of going to the universal cover, so there are these 2 closed curves. Let's say genus so you have a finitely many curves, and then the complement is simply connected. So if you condition on a choice of these 2 curves, then isn't the theory reduced to the simply connected case which you have already?
So let me understand. So you want to condition on branches of the UST, and you want to...
Before, I mean, so basically instead of the UST, it's UST with rooted along some cycles, right? So
yes,
once,
so for example,
so if you,
yes,
so there is one edge going from one boundary component to the other.
No, actually. So here it's going to be a cycle rooted spanning forest. So your forests are going to have some components which has cycles like this. And there could be a whole lot of cycles here. So this is the problem, because since we had this radial SLE description of the branches to the boundary, I'm not aware of any nice description of these cycles. So this, I mean, this SD description or any description like this of these cycles. So this is one issue to explain.
I see. What if you, instead of taking cycles, suppose you look at a path from the inner boundary to the outer boundary and you condition on that?
Yeah, in that case, I think it's known that it's GFF. So at least in the annulus case, for example. So Kenyon's work, I think, so there, if you have a path, then you can actually define height functions. There won't be an instanton component or anything like that. And then it's known that this height function will converge to the GFF on the annulus.
Okay.
So that's, at least for the square lattice, that's known.
Okay. Okay, thanks.
Yeah.
Other questions? Right, if not, so we thank Gourab again and for this great mini course.